Button that up a little bit. Good morning, guys. All right. I apologize. This 8 a.m. thing is a little bit early for me too, so we're gonna make it work. So give me just a few seconds to get my dog camera set up. Okay. Some fresh paper. And we are ready to get started. All right. So last time we looked at a handful of substitution problems. I wanted to look at just one or two more slightly challenging ones. But also to introduce the more geometric stuff that we're supposed to be doing later in the week. So this, of course, let's get this set up. Yeah, good morning. QCam, let's get that talking. Oh. So last time we went through the syllabus, we talked about all the course policies. If you missed class last time, please go ahead and take a look at the video that I recorded of our lecture on Monday. And that way we don't need to burn time today doing that same thing. The other two sections that we need to talk about this week are 6.1 and 6.5. 6.5 is kind of trivial. There's a little bit of fun stuff to talk about there, but there's nothing really challenging conceptually. 6.1 has a little bit of geometry stuff that some people find a little bit tricky. So I want to talk about section 6.1 first. And you might be thinking, well, what about 6.2, 6.3, 6.4? Don't worry, we're going to cover those next week. 6.2 and 6.3 are good extensions of 6.1, but they're totally disconnected from 6.5. So don't panic. So first we're going to cover section 6.1, which is areas between curves. The basic idea is this. Maybe you have one function here, we'll call it f of x. And you have some other guy here, we'll call him g of x. And you'd like to find the area between f and g from x equals a over there to x equals b over here. I'd like to find this area. That's the idea. The lazy way to do this is to say, okay, well, I'm just going to take the difference of, or the absolute value of the difference of f and g and integrate that from a to b. That will do the job. That's the formula your book has. So the area between y equals f of x and y equals g of x on the interval ab is the integral from a to b of the absolute value of f of x minus g of x. But I would bet dollars to pesos that most people do not know how to integrate the absolute value function itself. And so this formula isn't especially useful unless you have a way of interpreting the absolute value that allows it to be integrated. And the more clever way to do this, I think, is to go ahead and identify anywhere that these guys trade places. So I'll call that C. And then you integrate the upper minus the lower. That's the idea. And this formula will give you that. The truth is that the absolute value of f minus g is either f minus g or g minus f. It's one of those two things. If f minus g is positive, if f is bigger than g, then the absolute value of f of x minus g of x is just f of x minus g of x. If f is smaller than g, so f of x minus g of x is negative, then the absolute value of f of x minus g of x is the negative of f of x minus g of x, which is g minus f. But in this case, I would say, I would write it like this, and this is how I would encourage you to go through these things. So this is going to be the integral from a to c of f minus g plus the integral from c to b of g of x minus f of x. Because from c to b, g is above f. And in general, you think of it as the integral of the upper function minus the lower function, or the larger valued function minus the smaller valued function. So let's grab a few fun examples, and maybe we can find one here that will also give us practice with our use of. We could do that. Yeah, let's do this. Yeah, this is a classic. Okay. So for our first example, we'll find area Let's see if we can find the area between sine and cosine.
Excuse me, sir. Can I take the picture of the first page?
Sure. Yeah, it's that's the important stuff.
Okay, thank you. Got it.
Were there any questions about coming from or why this formula is what it is? I guess before we move on. Really, the one way to justify this formula, if you're not 100% clear on where this is coming from, you think about the area here underneath F, and then we just subtract out the area that's underneath G, and that will leave us with the area between them. So that's what this integral is doing. It's calculating the area under F from A to C, and then it's subtracting away the area under G from A to C. Okay. So we want to find the area between sine and cosine from 0 to pi over 2, so we should sketch a graph. So let's we'll do sine first. Mark this up here as 1. And sine. We'll come back over to 0 there. So yeah, we should maybe make this pi over 2. That's lots of space. Like that. And you know, sine continues over here like this. That would be pi, and so on. And cosine. This is pi over 2, nice big fat point there. Cosine would continue like this. So this is sine x. This is cos x. And we want to find the area between them from 0 to pi over 2. So that's this area. And I do apologize here, my graphs didn't end up touching at the perfect point, but imagine this is pi over 2. We need to find this value where sine and cosine are equal between 0 and pi over 2. If you think about your unit circle where sine and cosine equal from 0 to pi over 2, that's got to be pi over 4. So in this first little chunk from 0 to pi over 4, cosine is above sine. So to find the shaded area here, I find all the area underneath the cosine graph, and then I subtract the area that's underneath the sine graph. In other words, I'll do the integral of cos x minus sine x from 0 to pi over 4. And then to that, we need to add the integral from pi over 4 to pi over 2. And now sine is on top, sine minus cos. Sine x minus cos x. Okay. Now, none of the antiderivatives here are hard. An antiderivative for cosine, a guy who differentiates to cosine, that's sine, minus a guy who differentiates to sine, well, that's negative cosine, and the two minuses will make a plus. And we evaluate that from 0 to pi over 4. And similarly over here, a guy who differentiates to sine, that's negative cos, minus a guy who differentiates to cos, that's minus sine. And this piece is evaluated from pi over 4 up to pi over 2. So now for the evaluation step, if I plug in pi over 4, the sine of pi over 4 and the cos of pi over 4 are equal to each other. They're both root 2 over 2. So at the upper limit, I get root 2 over 2 plus root 2 over 2. And then I have to subtract what I get when I plug in my lower limit. When I plug in 0, sine of 0 is 0, cos of 0 is 1. So that's this first piece evaluated. Plus, if I plug in pi over 2 here, cos of pi over 2 is 0, sine of pi over 2 is 1. So this will be negative 0 minus 1. And from that, I have to subtract what I get when I plug in pi over 4. So this will be minus, and then when I plug in pi over 4, I'll get negative root 2 over 2 minus root 2 over 2. So now we want to combine all our like terms. Root 2 over 2 plus root 2 over 2, that's just root 2. So this is root 2 minus 1. Minus 1, here if you subtract these, negative root 2 over 2 minus root 2 over 2 is negative root 2. With this minus becomes a positive. So altogether we have 2 square roots of 2. And then minus 1 is minus 2. So not terribly complicated. Any questions about this example, how we set this problem up, why it worked out the way it did, where the picture came from? I'm sorry for my bad art. I know it's early, but try to summon some thoughts if you have any. Any questions or concerns, doubts? Anything not 100% clear or obvious?
So on that pi over 4, are both of those areas equal there?
Let's see, that's a good question. So this is negative 1 plus root 2. And this comes out to negative 1 plus root 2. Yeah, there is a symmetry here. My bad drawing kind of hides it, but yeah, this area and this area are equal.
Will we typically be seeing this kind of thing with like trig problems or?
Certainly it's possible, yeah. Trig is a big part of calc, and trig functions provide a basis for some of the most important examples in calc. So I would certainly expect to see trig all throughout the class. And then Griffin, yeah, the reason this minus is coming in here is because we plug in the upper bound here, and that gave us these. And then we subtract what we get when we plug in the lower bound to these. And when I plug in x equals 0, the sine of 0 is 0, the cos of 0 is 1. Okay, these are good questions. Why are there two squares on both sides of the equation? Well, when I plug pi over 4 in to this expression, I get root 2 over 2 here. The sine of pi over 4 is root 2 over 2. And the cos of pi over 4 is root 2 over 2. So each one of these gave me a root 2 over 2 when I plugged in pi over 4. I guess if we want to see the intermediate step there in the evaluation, I can show that. So this is going to be sine pi over 4 plus cos pi over 4 minus sine 0 plus cos 0. That was this first block. And then to that, we had to add negative cos pi over 2 minus sine pi over 2 minus negative cos pi over 4. I'm going to run out of space, minus sine pi over 4. Like this. So that's the step that came in between here and here. Yeah, you plug in the upper bound, and then you subtract what you get when you plug in the lower bound. Exactly. Good questions. Anything else on our mind here? The idea behind this process is basically taking a function to be larger over the other and subtracting this one. Yeah, exactly, Nick. Yep. Yeah, so maybe I should explain that picture a little bit more thoroughly. Imagine I just started with the area under F from A to B. Usually when I do this lesson, I have a big whiteboard and lots of markers and colors. So here, I don't quite have that, but I can try to mimic. So here's f of x. And the integral from a to b of f of x dx is this area. If I toss in g, the integral of g, well, let's see. So here's my c. So if I integrate f from a to c, I would get the area that is cross-marked like this. And then if I subtract off the integral of g from a to c, so let's think just about this region here. If I'm only after the stuff that's in the middle, I should take the integral from a to c of f of x dx. That's all the stuff that's like this, and then subtract off the integral from a to c of g of x. And that you can combine as the integral from a to c f of x minus g of x comes together as the upper minus the lower. And that's what will give me this region in the middle. I take all of this area and then I subtract off this area. And you can combine those into a single integral like this. On the other side, g is larger. So if I take all the area under g and then I subtract off the area that's under f, that will just leave me with this stuff that's in the middle. So over here to the right of c, I take the integral from c to b of g of x, and I subtract off the integral from c to b of f of x. And that combines to integral c to b of g of x minus f of x dx. So that's kind of where this is coming. I think it's a lot easier to see with color than it is with the cross hashing, but hopefully you can kind of see what I'm saying here. To get the area that's in between the two, you take the area underneath the upper guy and then subtract off the area underneath the lower guy. And you can always combine that into a single integral. So it's always the integral of the upper minus the lower. There is a way that this can get a little bit weirder. And that's if instead of having your functions use x as their independent variable if your functions use y as their independent variable. And the whole picture kind of rotates 90 degrees. But let's look at one more slightly simple example like this before we move out of that setting. Yeah, exactly, Griffin. Yep. Oh, so that's not bad. Oh, they go straight to the right minus left stuff. Okay. Let's look at number 9. So I want to find the area bounded by the 3 curves, or the 3 equations, y equals 1 over x, y equals 1 over x squared, and x equals 2. So we better know what 1 over x and 1 over x squared look like. 1 over x is this hyperbola. 1 over x squared is, so let's call this the point here, 1 comma 1. 1 over x squared starts out above 1 over x, but then comes in, they cross right at this 1, 1 point, and 1 over x squared sits down harder. So let's call this 2. Okay. So something like this. And then the line x equals 2, that's a vertical line right here. So the region they're looking for is this one. So this guy is 1 over x. And this guy, the dark guy, is 1 over x squared. Between 1 and 2, 1 over x squared is underneath 1 over x. So here, the area between these curves, this is going to be the integral from 1 to 2 of, who's my upper? My upper is 1 over x, minus my lower is 1 over x squared. So then an antiderivative for 1 over x, ln x works. I guess I should really be using ln of the absolute value of x if we're careful. That's the rule, right? Integral 1 over x is ln absolute value x minus, what's the integral of 1 over x squared? What is an antiderivative for 1 over x squared?
We can rewrite it as x to the negative second
Mm-hmm.
integral.
Okay. All right, let's maybe do it like that then. So I'll split this up. I'll treat it as the integral from 1 to 2 of 1 over x dx minus the integral from 1 to 2 of x to the negative 2 dx. And then the 1 over x piece, that will become the ln minus, and so then what is the antiderivative here? If I use my power rule on that x to the negative 2, what goes in here? What is an antiderivative for this? Yeah, 1 over x, right? We add 1 to the power and divide by that new power. So this would be x to the negative 1 divided by negative 1, or negative 1 over x. And then he also gets evaluated from 1 to 2. We can do ourselves a small favor with the minus signs. I can pop this minus sign. This minus sign can pop out and combine with this to make a plus. So this will be ln absolute x from 1 to 2 plus 1 over x from 1 to 2. And I'll give myself a little dividing line here and say, all right, we're going to come back up over this way. When we get to doing our evaluation, I'll plug in the upper bound and then subtract what I get when I plug in the lower bound. So this will be ln absolute 2 minus ln absolute 1 minus 1 over 2 minus 1 over 1. What's the ln of 1? No, it's neither e nor 1. Yeah, it's 0. 0. The natural log of e is 1. The natural log of 1 is 0. ln2 is not a nice number. We can just leave it as ln2. And then from that, we need to subtract this, which is 1/2 minus 1, or negative 1/2. So it'll be minus negative 1/2 is the same as plus 1/2. Oh, thank you. Yeah, good catch. This plus, this should be a plus, which means this will stay a minus. All right, 1/2 minus 1, yeah, minus 1/2. Thank you. Yeah, this plus is this plus. So those should still be there. And then 1/2 minus 1 is negative 1/2. So it's ln2 minus 1/2. Thank you. Yeah, good catch, David. Okay. So this is the main feel for 6.1. It's not terribly hard. Some of the problems you have in your homework will ask you to come in here and draw an approximating Riemann rectangle. So if you wanted to, you could sketch it like this. You know, if we were going to come up with Riemann sums for this integral, we could draw a rectangle in like that, which would be one of my little Riemann rectangles. Hari, what was the question? Oh, what was I originally going to do? I was going to do the antiderivative step in a single move here. But it seemed like we were, as a class, having a hard time coming up with an antiderivative for 1 over x squared. So right here, I was going to write ln absolute x minus 1 over x. But we needed a little bit of time to come up with that. So I instead decided to split the integral into 2 pieces and let everybody take their time with this integral. Okay, cool. So yeah, if you were asked to come in here and draw a little approximating Riemann rectangle, it would look like that. Because if you were building a Riemann sum for this thing, you know, you would have a bunch of these little rectangles like this. And drawing the graph by hand is probably the most important part of this section. Make sure you take your time to draw the graphs by hand. And they don't have to be beautiful, perfect pieces of art. Mine certainly are not, and I would not hold you to a standard that I can't hold myself to. But you need to know the shapes of these graphs. You need to know, for example, that the 1 over x squared graph starts out above 1 over x and then comes down below 1 over x. Those are the sort of things that you can develop intuition for by playing around in Desmos, and you should do a lot of that. So if I didn't know off the top of my head what those graphs look like, I would come in here and just do this. And then I would zoom in over here And you see, oh yeah, so 1 over x squared starts out above 1 over x and then gets beneath him at 1. And the 1 over x is this hyperbola that we know pretty well. So from here to here is not hard. But you want to get to a place where you can do this on your own without the help of Desmos. So that family of power functions, x to the n, we should know all of those. We should know all of those graphs really well. There is another setting, like I mentioned. What if our curves are functions of y rather than functions of x? So maybe my setting is something a little bit more like here's f of y, and here's g of y. How could I find this area? And the answer here is to just turn your head sideways. Right, it might sound silly to say it, but just rotate the whole picture 90 degrees. This guy looks like my upper, and this guy looks like my lower. So really, it would be rightmost minus leftmost, because the increasing direction of x is this way. So going to the right in this setting is like going up in the original setting. The other things you would need are these y values. I guess I should call that guy B. He's the larger one, and call this guy A. So here we would integrate from A to B. Let's see, who's my rightmost? It's G. And in general, you would integrate from wherever to wherever, the right minus the left. And these integrals are done dy. And if you had to draw in a little approximating Riemann rectangle, it would look like this. So I think we do have some examples that kind of look like this. Let's see what we can find. Won't spoil any of those. Yeah, here, let's do this one. So they say find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. For sure, the slightly strange thing here is that parabola, y squared equals 2x plus 6. We're not used to seeing those with the y squared. We're used to seeing those with the x squared. Because it's the y that's squared here, you're going to be opening left to right rather than up and down, just like in that picture I drew a second ago. And in fact, because it's a positive y squared, you can be confident this parabola will open to the right. But I'll show you a little bit how to sketch these, even if you don't know or don't remember the study of conics from pre-calc. 2x plus 6, I can actually factor a 2 there. That's 2 times x plus 3. So you can ask yourself, if y is 0, then x would have to be negative 3. And if x is going to be 0, then y squared would have to be 6. So you can plot a few points. Let's see, when x is negative 3, so I'll mark that over here. 1, 2, 3. We know this guy is on my parabola, negative 3, 0. And I also know that if I plug in x equals 0, I get y squared equals 6. So plus and minus the square root of 6. So maybe root 6 is, let's see, root 4 is 2. So 1, 2, 3. So the square root of 6 is going to be somewhere around here. So this parabola, something like this guy. And then your line y equals x plus 1. You know he looks like this. So that's a reasonable sketch of this. And then the other y-intercept here is at negative root 6. So the area we're looking for is this area. And because we're in this setting where our functions are functions of y, x is given as a function of y rather than y being given as a function of x, it makes most sense for us to do the integral dy. The only other two things I need then are the bounds. So I want to integrate the right minus the left, and the integral will be done dy. But the question is, what's a and what's b? Just ain't enough coffee in the world. Well, these should be y values. And the lower bound is whatever this y value is. And the upper bound is whatever this y value is. Because I think about my Riemann strip as moving through the region like this. So it starts off down here at y equals a, and it moves up here to y equals b. So in order to find those two bounds, I need to set these equations equal to each other. It might be helpful to solve them for x first. We're going to have to do that anyway. So let me go ahead and do that. In this guy, this is the same as saying y squared minus 6 equals 2x. So 1/2 y squared minus 6 equals x. And this one's the same as saying y minus 1 equals x. So here's my line solved for x. Here's my parabola solved for x. If I set these two, y minus 1 and 1/2 y squared minus 6 equal to each other, that will locate for me these two intersection points. The smaller of those two intersection points will be a, my lower bound of integration. The larger of those two intersection points will be b, my upper bound for integration. And then I'll integrate the right minus the left. The right function is this one, so it'll be y minus 1. And the left is this guy, the parabola. Because everywhere in this region, the parabola is to the left of the line. So let's find those intersection points.
Excuse me, sir. How do you know the function is left or right?
From the picture, right? So that's the point, is I took my time to draw this graph, and then from the graph, I can deduce that. So this is coming from the function x equals 1/2 y squared minus 6. And this guy is x equals y minus 1. So I draw the picture. I recognize that the only region that's enclosed by these, the only closed region that has a fixed finite area is this like bloopy region here. And everywhere in this bloopy region here, the parabola is to the left of that line. If I look at any particular y value, the parabola is always to the left of that line. So this is my right function, and this is my left function. Does everybody see that? Because in this region, if you take any fixed point, the line is to the left of the parabola, or sorry, the line is to the right of the parabola. So let's find those intersections. Let's see, where do I have space to do this? I'll do it here. Let's find the intersection. So I'm going to take this guy and set it equal to this guy. Can multiply both sides by 2. Distributing the 2 on the right. And now I can pull everything to one side. So this will say y squared minus 2y, and then minus 6 plus 2 is minus 4 equals 0. And then I can factor this. Let's see. Oh, can I factor that? So I need two numbers whose product is -4 and whose sum is -2. Those might not exist. No, those might not be nice numbers. Let's see. It's early. But no, I don't think those are nice numbers. I think these might involve the square root of 3. So we could use the quadratic formula, or we could complete the square. It's probably been a while since you guys have seen how to complete the square, so let's go ahead and do that. This is y squared minus 2y plus 1 minus 1 minus 4 equals 0. And then this piece is y minus 1 all squared. And then this is minus 5. So this is the same as saying y minus 1 squared equals 5. So y minus 1 is equal to plus or minus the square root of 5. So y is equal to 1 plus or minus the square root of 5. So those are our two intersection points. A is 1 minus the square root of 5, and B is 1 plus the square root of 5. So then, the integral we need finds this area. will be the integral from 1 minus the square root of 5 to 1 plus the square root of 5. The right minus the left. The right is y minus 1 minus the left is 1/2 y squared minus 6. And the integral is done dy. Does everybody see where everything is coming from here? Those intersection points ended up being a little nastier than we would have liked. When you get to this step, you could also use the quadratic formula. Right? So I chose to complete the square to solve that equation. So these steps might look a little bit foreign to you unless you remember completing the square. But you could also use the quadratic formula. Questions on where these bounds came from?
Excuse me, sir.
Yeah.
Where you wrote find intersection point, is it 1/2 factor y squared minus 3 or 6?
Minus 6, right? Yeah.
Because we move out on the top 2.
So you subtract the 6 from both sides and then divide both sides by 2. You could write it as 1/2 y squared minus 3 without the parentheses. But if you're going to have the parentheses here, if you solve this equation for x, you would subtract the 6 and then divide everything on both sides by 2.
Okay, thank you.
So if you wanted to, you could write it as 1/2 times y squared minus 1/2 times 6, and that would give you a 3 there. But as is, it's sound here, it's correct. So my first step here wasn't distributing this, it was to get rid of the 1/2. I multiplied both sides by 2. Okay. So this is the integral we need to compute then. I'll try to leave as much of this picture here as I can. All right. We can distribute this and combine like terms. I'll have negative 1/2 y squared. Just going to try to write this polynomial here in standard form. So the quadratic term will come first. I'll have to distribute the negative and the 1/2. Negative 1/2 times negative 6, that's positive 3. Positive 3 minus 1, that will be my constant term. It's positive 2. And then my linear term will just be plus y. And then minus 1 and positive 3 is positive 2. So from this line to this line, I'm just simplifying algebraically. I distributed this 1/2, and then I combined all my like terms. 1/2. Yeah, remember the left function is 1/2 times y squared minus 6. So I'm integrating my right minus my left. So this down here, sorry, maybe you're asking about this one. This is a 1/2. And now we're ready for our antiderivative step. I'll add 1 to this power and then divide by that new power. 2 plus 1 is 3, so this will be negative 1/6 y cubed. So I've already got a 2 downstairs. Plus 1/2 y squared plus 2y. And that's what I'll evaluate from 1 minus root 5 to 1 plus root 5. And then we can plug these bounds in and subtract. Of negative 1/6 times 1 plus the square root of 5 cubed plus 1/2 times 1 plus the square root of 5 squared plus 2 times 1 plus the square root of 5. That's plugging in the upper bound. And then from that I have to subtract what we get when we plug in the lower bound, which is 1 minus root 5. So it'll be negative 1/6 times 1 minus root 5 cubed plus 1/2 times 1 minus root 5 squared plus 2 times 1 minus root 5. And it might look like this is horrendous and impossible to clean up, but it's not. It's not super nice, but it's not super horrible either. The cubic terms are a little bit unpleasant, but I would be okay with you leaving it like this. Maybe the only obvious things to clean up here, I've got 2 plus 2 root 5 minus 2 minus 2 root 5. So it's a matter of taste how far you want to go to clean things up from here. I don't want to burn too much time just doing arithmetic. Yeah, so maybe we'll just leave it like this. You could combine some things if you wanted. You got a negative 1/6 times this quantity cubed. Yeah, it's not the same as these. They're not like terms. I would just leave it like this, honestly. Cleaning this up from here is not a super pleasant thing. It's not super enjoyable. It doesn't really teach us very much. So you could leave it like this. That would be okay. Let's maybe we'll distribute everything, the negatives here. So I'll call this negative 1/6 times 1 plus the square root of 5 cubed plus 1/2 times 1 plus the square root of 5 squared plus 2 times 1 plus the square root of 5. And then we'll have minus makes plus 1/6, 1 minus the square root of 5 cubed. This minus will come here to make minus 1/2, 1 minus the square root of 5 squared, and then minus 2 times 1 minus the square root of 5. That would be my first step cleaning this up. And then if you really were patient, you could FOIL out 1 plus root 5 cubed and 1 minus root 5 cubed. And there will be a meaningful amount of cancellation between these two terms. For example, the 1 and the 1 here will give you a 1/6 and a negative 1/6 here. Those will cancel. But I would be okay with you leaving it like this. And WebAssign would accept this answer too. The big deal here is getting to a place where you can set up the integral. So what I would like to do, I don't want to get in the way of anybody who's still writing. But what I would like to do is come back to this first page here and make sure we're all comfy with the steps that led to this integral. So first, I'll just give a few seconds for anybody who's still writing here. Okay. So then questions on this setup, questions on what led us to that integral. Are we all comfy with where the picture came from? All the things that led to this integral here? What are we wondering? What are we thinking? Let's do it like this. if the line was sloped the other way, say still had a y-intercept of 1 but ran like this, the line would still be the rightmost function. It would go largely the same. Your bounds would definitely change because that would change where the parabola and the line intersect. But most of the setup and most of the picture would go the same way. The line would still be the rightmost function and the parabola would still be the leftmost function unless you also moved that y-intercept. Other questions on this guy? Okay. All right, I think we've got time to do one more here. So let's grab one more fun problem to work on, and then I will let you guys go for today. Remember, your homework in WebAssign is up, and it's important that you're working on that already. Don't waste any time getting to it. Let's look at what looks nice and challenging. No, that's cool. Oh yeah, the office hour discussion. So let me show you where I am with that. This is what I've determined so far for office hours. So on Tuesdays, I would do the 12 to 1, and I'm contemplating the 8 to 9. And then on Thursdays, so I think what I'll probably end up doing is I'll take this one for Tuesdays and then this one for Thursdays. I'm not 100% sure there, but yeah, I will have an office hour this afternoon from 3:30 to 4:30. And I'll get those links up in Canvas during my free time here. So let's look at 32. This is, yeah, log x over x. So in 32, they want you to find the area between log x over x and log squared x over x. These are these two functions. You would be forgiven for not knowing off the top of your head what either of those graphs look like. These are both pretty complicated. The blue guy is log squared x over x, or log of x all squared over x. And the red guy is log x over x. So the area that's enclosed between them is this region here. So we would have to find these intersection points, and they're not super obvious, but we can cook them up pretty easily. So we come back to the .cam. We can copy our sketch over a little bit, so. Okay, yeah. This is y equals ln x over x. And then log squared x over x comes down from above. Does it come all the way down? Yeah, he does. bounces. Comes up, switches to concave down somewhere here. This one is y equals ln x squared over x. So the region I'm looking for the area of is this guy. And just like in the other problem, we need to find the intersection points, these guys. So I'll set ln x over x equal to ln x all squared over x. Neither of these guys are defined at x equals 0, so I know 0 isn't either of those intersection points, which means I'm free to multiply both sides here by x. Which gives me this. And then there's a couple ways you could think about this. You could imagine making a little substitution in the equation. Or you could, what's the right way to say this? You could pull everything to one side and factor. And then if you factor an ln x out from this, what's left here would be ln x minus 1. Yeah, anytime you have something is equal to that same thing squared, the two solutions will come from when that thing is 0 and when that thing is 1, but this is how we discover it. So subtract ln x from both sides and you get this, and then factor ln x and you get this. So either ln x is equal to 0 or ln x is equal to 1. Ln x is equal to 0 at two places. Sorry, ln x is equal to 0 at one place. That's when x is equal to 1. And ln x is equal to 1 when x is equal to e. So these are our two x values where we intersect 1 and e. So my integral, so the area, is going to be the integral from 1 to e of my upper minus my lower. Everywhere in this region, this curve, ln x over x, is my upper. And ln of x all squared over x, that's my lower. And this makes for a good integral to round up the day because this requires some substitution. Right? So how do we find this integral? How do we calculate that guy?
Should we make u equal to ln of x?
Mm-hmm. Yeah, good. So if you want to, and I would consider doing this if I were you, I'd write this as ln x minus ln x all squared times 1 over x dx. All right, you can factor the 1 over x inside your integral. And then make the little substitution. U equals ln x. Du is going to be 1 over x dx. And also our bounds will change. When x is equal to 1, u is equal to the natural log of 1. which is 0. And when x is equal to e, u is equal to the natural log of e, which is 1. So there's all the stuff for my substitution. And I get that this integral is the same as the integral from 0 to 1 of, well, ln x, that's u, minus ln of x all squared, well, that's u squared. And then 1 over x dx, that's exactly du. So every piece here is important. It's important that you remember to change the bounds. When x is equal to 1, u is equal to the natural log of 1. Oh, well, the natural log of 1 is 0, so my new lower bound is 0. And when x is equal to e, u is equal to the natural log of e. So the natural log of e, oh, that's 1. So my new upper bound is 1. The 1 over x dx piece right here, that's exactly du. That's why I factored the 1 over x out. Each of these had an x downstairs. So I could factor that x downstairs as a 1 over x and group it with the dx here for my substitution. And then this is u, and this is u squared. So what we end up with here take my antiderivative. Antiderivative for u is 1/2 u squared minus an antiderivative for u squared is 1/3 u cubed, and I'll evaluate that between those new bounds, 0 and 1. The magic of changing your bounds, you don't have to go back to the old variable. When I plug in 1, you get 1/2 times 1 squared minus 1/3 times 1 cubed. And then when I plug in 0, I get 1/2 times 0 squared minus 1/3 times 0 cubed. That's all 0. So this is just 1/2 minus 1/3. So what is that? That's 3 over 6 minus 2 over 6. That's 1 over 6. Excuse me. Still too early for me. But yeah, so these areas between curve problems, not terribly hard. It all comes down to having a reasonable graph. And your graphs don't have to be works of art, but they do have to be clear enough that you can kind of see what's going on. You can tell which function is above or below, or to the left or to the right of the other. And you should be able to spot where your intersection points are, at least double check that the answers you come up with when you solve for your intersection points are reasonable looking. And then from there, the integrals are all integrals that we've done before. There's no new integration methods here, but you will have lots of opportunity to practice your substitution and power rule skills. There is also a meaningful amount of trig. If there's one problem in the homework that I would expect to give you a hard time, let's see, is this it? No, it's old. If there's one in here that I would expect to give you a hard time, it is, come on. 1, fault 20, that's you guys. I don't think you'll have a hard time with any of those, but this fella tends to be a little bit tricky. So I would say take your time when you go to draw this picture. Take your time, maybe use a little Desmos. It's okay if you use Desmos to help you draw the graphs from time to time. And then make sure you know where your intersection points are, make sure you're comfy with how everything looks. So draw your picture nice and big for number 22 in the homework. I don't think any of the other ones here will give you an especially hard time. Friday, we're going to talk about average values. So don't worry about 23 through 25 yet. I haven't told you how to do those. But everything else, we should be able to get in here and get working on. So all of these are pretty straightforward. Up through 16, those are all just practice with U sub. And then 17 through 23, those are practice with areas. And then the last few are average value problems, which we will talk about on Friday. They're not anything hard. It's just kind of a formula that you have to follow, but there's a neat picture that goes along with it, and there's some ways of interpreting that picture in statistics that you might find interesting, especially if you're going down a road that leads to more stats. So this is where I'm going to leave it for today. I'll get the video from today's class up as soon as I can, and then I will have an office hour this afternoon at 3:30. So watch, I'll update our Canvas page if you want to come by that office hour and work on some problems or talk about anything. I'll have that info up there for you guys, and then we can come hang out in Zoom if you'd like. All right, I am going to go ahead and end the meeting here. Like I said, if you have any questions, come by the office hour, or you can always shoot me a message on Canvas. That's a good way to get a hold of me too. Okay, bye guys.